Hi, I'd like to introduce you to Team 23's presentation, a reproduction study of explainable automated coding of clinical notes using hierarchical label-wise attention networks and label embedding initialization. This is also paper 52. The team is comprised of my teammate Benjamin Oshawer and myself, Neil Patel. Before diving into the main topic of this paper, I'd like to take a moment to talk about what clinical notes actually are. Clinical notes are used to provide a standardized approach to access disease information across all patients at a global scale. They have a variety of applications, including audit, medical care, and research. While these codes are essential to provide systematic healthcare across the globe, they're built on a system that is not easily scalable and can lead to significant overhead to maintain. In most cases, these codes are manually maintained by medical personnel. As with most manually intensive processes, there is significant room for error. This can potentially jeopardize the system, which is responsible for the well-being of patients in care around the globe. On this slide, you can find two facts about medical codes. One, there are on average 16 unique ICD-9 codes per medical summary. ICD-9 is the standard system for diagnostic and procedures used in hospitals across the United States. Two, the medical code for pneumonia is linked with acute respiratory failure on over 3% of cases across a large database spanning 55,000 records. Now, I would like to introduce you to the paper's novel solution, which is a hierarchical label-wise attention network, also known as HLAN. This is the paper's novel solution to automated medical coding. The key features are that it highlights segments of the medical notes, which ties back to the model prediction, as well as both word and sentence level attention sensitivity. For the scope of our reproduction study, we will be recreating the HLAN model with label embedding on the Mimic3 Top 50 code dataset. We hypothesize that we will have inferior performance to the model from the actual paper. We will have a positive signal from our model, but it likely won't be as strong, and this is due to the limitations of our reproduction study. For this reproduction study, we weren't able to replicate the hardware used in the original paper. For this reason, we had to significantly reduce the number of epochs ran for each of the performance tests. As a result of this, the model was not trained as thoroughly or as intensely as was done in the original paper. Our methodology for this reproduction study can be broken down into four main pieces: model, dataset, implementation, and code. Here you can find a picture of the HLAN model architecture. It's composed of an embedding layer, hidden layers, and prediction layer. The embedding layer takes the one-hot representation of each word into a low-dimensional continuous vector, where one-hot representation is transformed by a weight matrix calculated from the word-to-vec Baga-Worth algorithm. A bidirectional GRU with attention is composed at both the word and sentence level. For the dataset, discharge summaries were sourced from the Mimic3 dataset. Each contained at least one of the 50 most frequent diagnosis or procedural ICD-9 codes and had a discharge summary for each visit. We also performed additional preprocessing steps, which include changing all characters to lowercase, removing numeric-only tokens, pruning punctuation, and removing words that appeared less than 3 times. The dataset was then split into a train, test, and validation split. The train file was comprised as follows: 8,064 discharge summaries, 1,572 summaries, and a test set of 1,728 summaries. For the computational implementation, we leveraged the TensorFlow framework utilized on standard CPU hardware across both Windows and Mac OS. Here we've also included a list of hyperparameters along with their values. These hyperparameters were tuned based on model performance, and these are the resulting values that yielded the best performance in our reproduction study. Regarding the code for our reproduction study, all software requirements and steps have been recorded on the GitHub. We leveraged the core implementation of the original study while making some adjustments to preprocessing and model tuning. Please refer to the GitHub repository shared in the references slide for more information. Here we have the aggregate error metrics. The study paper was trained on 100 epochs and performed better on the AUC and macrometrics. Our reproduction study was trained on 25 epochs and performed better on the micrometric of the AUC, precision, recall, and F1. The macro-micro performance split is not surprising. The macro performance metrics are typically used for datasets with more class imbalance, and the top 50 ICD dataset code is indeed class imbalanced. The most frequent code occurs over 3,000 times, while the least occurring code occurs around 400 times. This class imbalance would place greater credence on the macro measures and would make sense why the paper outperforms a replica, as it has many more epochs to tune on. This waterfall graph shows the difference in F1 performance per label, comparing the study paper with our reproduction implementation. The codes at the bottom are arranged from most frequent to least frequent. Observe that most differences were less than 5 points. There were a few outliers where there was a 20+ point difference. Overall, labels in our reproduction study performed slightly worse. 27 labels had a decrease in F1 performance, while 23 labels had an increase. Comparing the study paper to our reproduction study, there was an overall downward trend of 30 points. On average, each label performed 0.6 points worse than the original study. To summarize, our results were indeed inferior to that of the original paper. This is mostly attributed to the fact that we didn't train as long as the study paper, and this is because we had a lack of computational resources. It was taking us around 2 hours to train a single epoch. While the pre-processing steps were not discussed in the paper and were only available via the GitHub repository, they were easier to implement. The steps were more straightforward to follow, and there were less issues getting it working. I will call out that we had a few issues with package deprecation as the paper is now a few years old. If the authors of the paper could introduce a more introductory model building approach, it would significantly help with future reproducibility studies. A lot of the implementation details were glossed over in the paper. Overall, the paper is reproducible. However, you will have to deep dive into the implementation yourself to build a thorough understanding of what is happening under the hood. Here we've included a references slide where you can find the study paper, associated papers, as well as our code repository link, as well as a link to the Mimic3 database. That concludes our presentation of our reproduction study. Thank you very much.